Yo, what's up everyone? Welcome back. Patrick here, moving on to the next question. So the cost function for a company producing X units is given by this equation over here. So 80,000 plus 1,200X. And we have to find these three different functions here. The marginal cost function, the average cost function, and then the marginal average cost function. Now notice in this case, the cost function, it's a pretty simple function. It's a linear function. It's not always going to be this simple. Sometimes you may get quadratic functions, cubic functions. But in this case, it's just a simple linear function. So notice that there's a fixed proportion, right? That's the fixed cost, the 80,000. And then there's a variable cost of 1,200. So every unit that you produce in the company, you're going to have to pay $1,200 per unit, right? Times X plus that fixed amount of $80,000. So let's find these other functions here. So the marginal cost function, now the marginal function of any function is just the first derivative. So notice that if we take the first derivative of this function, the derivative of the constant is just going to be 0, and then the derivative of 1200x is just going to be 1200. And notice that what does the marginal cost function give us? It gives us the change in total cost per additional unit produced. And in this scenario, that makes sense because the total cost is going up by $1,200 for every additional unit that you produce, basically the variable cost, right? So the marginal cost function in this specific case, it's just a constant. It's just going to keep going up. That total cost is going to keep going up by $1,200 for every additional unit that you produce. Now, number two, the average cost function. Now, the way you get the average cost, let's say that we produce 5 units. So what would be the total cost of producing 5 units? Well, we would just plug in 5 for this X value. So then we have 1,200 times 5, which is 6,000, plus the 80,000, which is 86,000. That's the total cost. And then if we wanted to get the average cost of that per unit, then we would take that total cost and divide it by the number of units produced, which in this case is 5, so we would get 17,200. Right? So the average cost per unit, if you produce 5 units, is 17,200. And this is continually going to change. So the average cost per unit is going to be different if you produce, for example, 10 units than if you produce 5 units, right? So it's not going to be a constant function like the marginal cost function. And so if you want to generalize this, basically this average cost function, what it's going to be is it's going to be the total cost, which is given by this function, so 80,000 plus 1,200x divided by the number of units, which is x, like that. So that's the average cost function right there. And sometimes you'll see this written in a different way. So sometimes they'll split this up into multiple fractions. So you'll have 80,000 over x plus 1,200 x over x, like that. And then notice that these x's cancel out there. So you'd end up having 1,200 plus 80,000 over x, like that. And then going back to that previous example I just did, if you plug in 5 for this x value in this function, you would get that 17,200. So this is the generalized function. So you could plug in any value for x and get the average cost per unit. One thing I want to mention is if we were to graph this over here, notice that this is just a reciprocal function, right? So notice that it's basically that parent function 1 over x that's been transformed. It's been vertically stretched by 80,000, plus it's been shifted up by 1,200 units. And we don't have to worry about any negative x values. So if we were to take this function here and if we were to graph it, notice that the C value is 1,200, so we know that the horizontal asymptote is going to be at 1,200. Notice there's going to be a vertical asymptote at 0, so it's going to be undefined at 0, and that makes sense because if you produce 0 units, then there's nothing really to average out. So this function, in this scenario, because we're dealing with producing a number of units and assuming that we can't produce a fraction of a unit, this function would start at an x value of 1, right? So at an x value of 1, if we plug in 1 for this x value, we'd have 80,000 plus 1,200, which would give us 8,000 or 81,200. So let's say that's like over here. And what's going to happen is as x gets larger, you're going to end up having a function like this, right? So it's going to approach that horizontal asymptote of 1,200. And so a lot of times you'll see in textbooks, they'll ask you what's happening as x gets very large or as x goes towards positive infinity of this function. So let me rewrite it. Well, notice that this portion is going to go to 0 because a number over infinity is going to be 0 plus the 1,200. You're just going to end up with 1,200. So that's what the function is approaching. You can see that graphically as well. And it makes sense conceptually because if you think about it, the more units that you're producing, the less relevant that this fixed cost is going to be because it's going to be spread out over a bunch of units. So when we produce 5 units, then it's still pretty relevant, right? Because the average cost was 17,200, which is a lot bigger than that variable cost of 1,200, right? So because you're producing such a little amount of units, 5, then this fixed cost is more relevant. It represents a bigger proportion of that average cost. But let's say that you were producing 10 million units, right? Well, now this portion is going to be a lot smaller, and that average cost per unit is going to be a lot closer to 1,200. And eventually, as you go to infinity, that average cost is just going to end up being the variable cost of 1,200. So thought I would mention that. And then the marginal average cost function, so I'm going to leave that over there actually, is actually just going to be the derivative of this function. Sometimes a notation for this, in certain textbooks, you'll see the average cost function be c bar x, like that. And so the marginal average cost function is just going to be the derivative of this. So if we put c bar, that first derivative symbol x, like that. And what's the first derivative of this going to be? Well, the derivative of the 1,200, it's just going to be 0, the derivative of a constant. And the derivative of this here, well, we can take this portion, let's do it over here. And we could rewrite it as x to the negative 1, like that. So we could bring the negative 1 down, so we'd have negative 80,000, and then subtract 1 from the exponent, we'd have negative 2. So it'd be negative 80,000 over x to the power of 2, like that. Right, so this would be negative 80,000 over x squared. That's going to be the marginal average cost function. And what this is giving us is the amount that the average cost function is changing for each additional unit produced. So it's actually giving us the slope of the tangent at each of these points here. And notice that it's always going to be negative for any positive x value that you plug in. And so what that means is basically that average cost per unit, it's actually going down, right? That's what this is telling us. And again, that makes sense because for the more units that you produce, that average cost goes down, it starts approaching that variable cost. It goes from, if you produce 1 unit, the average cost is going to be 81,200, and it starts going all the way to 1,200 as x goes towards positive infinity. So it makes sense that this is negative. It means, what this means is that the average cost per unit is always decreasing with more production. All right, just in case they maybe ask you to interpret the results of all this stuff, I wanted to dig in a little bit more deeply in what all this means. But if you're given a cost function, that's how you find the marginal cost function, the average cost function, and then the marginal average cost function.